Hello students, welcome to the course of Data Communication and Networks. I am Dr. Munir Omar. Today in our lecture, we will study about the error correction. In the last lecture, we studied about the error detection. So now we will look into this topic. The main objectives of this is to know about the methods for error correction or the approaches which are used for error correction. And we will also study about the classifications of the algorithms used for error correction. Then we will learn about the Hamming code and understand the procedure of code word generation by using the Hamming code algorithm. So we will have one example for Hamming code and we will process that example by using the steps of Hamming code algorithm. So these are the contents for our today's lecture. First, we will revise the error and types of error, then error detection, the methods for error detection. We will have a quick look about these previous topics, and after that, we will start the error correction, the methods for error correction, and also the classification of algorithms used for error correction. Actually, there are many algorithms. We will give only the classes of these algorithms, and after that we will have Hamming code, and we will study this Hamming code in detail with an example. Now we are going to have a quick revision of error detection, which we studied in our previous lecture. First, error. It is obvious that the transmission medium is not perfect. So whenever we transmit data, that data may get scrambled or may have some sort of interaction with noise. So there might be some impairments. So the data might be get corrupted, which has been transmitted by the sender, and at the receiving it, the data might be different from the sent. So that thing is referred to as an error. For reliable communication, errors must be detected and corrected. So this is obvious, and this is the need of communication systems to get the corrected data before the processing of data. So these are performed, the error detection and correction are performed at data link layer and transport layer. Data can be corrupted during transmission, and most of the applications require that errors be detected and corrected. Two types of errors: single bit error and burst error. In single bit error, we say that there is only one bit which has been changed or which has been corrupted, and that is different at both the sides, the sender side and the receiver side. So this is known as single bit error. Only one bit at any place is changed. So then we have burst error. Burst error means that there are more than one bits, and these are not consecutive, and the length of burst error is measured as the starting bit and the ending bit. More than one bits then may not consecutive, and the third thing is the length should be measured from starting corrupted bit until the last corrupted. So this is the length of this error. Then error detection. Error detection codes are used. These are actually some additional data which is attached with the original data, and this additional data is used to help us detect the error in the original data. So this slide shows the concept of encoder and decoder. Actually, we need redundant bits or some additional bits to be attached with message. So for the generation of these redundant bits, we use a generator, and that generator is applied on the message. At receiving end, the same procedure is applied, and here the checker is used instead of generator, and this checker uses the same algorithm or the same method adopted by this generator to verify the status of data, whether it is correct or not, whether it is according to the sent data or not. So we need redundant data. The simplest way is to send two copies of data, but that thing would double the transmission time, and also the computation time will be slower as compared to normal case. So we can add some additional information with the message to help the receiver detect the errors in the data. Shorter group of bits may be added to each packet. These these additional bits are used by the receiving device to detect whether there is any error or not, and once the process is done, these additional bits are discarded by the receiver. So here we have data. Some additional bits are generated by a function, and these bits are appended with the actual data and sent. So with the help of these bits, the receiver check the status of the received bits and decide whether to accept or to reject. There are four types of redundancy checks. The first one is VRC, second one is LRC, then CRC, and checksum. For VRC, CRC, we use parity bit. Parity bit is an additional bit to be attached with the data to make the number of ones either even or odd. So if we need even parity, and most of the systems even parity is needed, so for that purpose one additional bit is added with the original data, and the value of that bit is decided by the number of ones in the data. Now here we have 1 2 3 4 5, we have 5 ones, so this is odd number of ones, so we must make it even by providing the parity bit equal to 1. So now here in this entire block we have even number of ones, so this is even parity. Error correction. The simplest way for error correction is to inform the sender about the status of transmitted packets, about the detected error, and ask to retransmit the data. So if the error is detected in the received packet, then the sender can be informed about the detected error and can be requested to retransmit that data. This is very useful method and very common in most of the data communication systems, but somehow it is costly because if the medium is highly prone to potential errors, then such type of requests for retransmission would be very high and the bandwidth will be lost on the retransmission of data. Then the best way to detect the error and then correct it at the receiver's end without acknowledging or informing the sender. The sender forwards the error correction code to the receiver along with the data. It is just like error detection, as we saw that with data some additional bits were sent for the detection of errors. So in the same manner, for error correction some additional bits or additional data is appended with the original data and transmitted towards the receiver. The receiver uses that appended data or the additional data or the code to automatically detect and correct the error. This type of error correction is more sophisticated than error detection, and also this procedure is more sophisticated than asking the sender for retransmission of data. To correct the error in data frame, the receiver must know exactly which bit in the frame is corrupt. To locate the bit in error, redundant bits are used as parity bits for error detection. So, before correction of bits, it is essential to know the corrupted bits, and for detection of corrupted bits, parity bits are used. There are two approaches for error correction. The first one is backward error correction, and the second one is forward error correction. So, we will discuss these two now in the coming slides. Backward error correction. This is the first approach we saw here. This approach is also known automatic repeat request ARR. The receiver device sends a request to the source device to resend the data after detecting the error or errors in the received data. More often used because it requires less bandwidth. But remember, if there are less chances of error, then it would require less bandwidth. But if the chances are higher, then it would require more bandwidth. A return channel is needed for backward error correction. So there must be some sort of mechanism so that the receiver also send the information about the received data to the sender. So for that purpose, the backward channel is also required. There are two ways for backward error correction. The first one is positive acknowledgement, and the second one is negative acknowledgement. In positive acknowledgement, the receiver returns confirmation of each block received correctly. The transmitter resends the block if that is not acknowledged. We have already studied about the acknowledgement, which is performed by TCP at transport layer. Then we have negative acknowledgement. The receiver returns a request to retransmit only the data with error. So, if the receiver detects an error, then it informs the sender. Otherwise, for correct data, no acknowledgement is sent or the sender is not informed about the correctness of received data. Then we have forward error correction. This technique allows the receiver to detect and correct errors without asking the sender for retransmission. The correction is made at the receiver's end, and for the correction, there is no involvement of sender. However, the sender adds some additional data with the original data before the transmission, and that additional data is used for detection and correction. The bandwidth requirement is higher, but return channel is not needed. If there is less potential, if there is less chances of error, or the medium is not at the worst condition, then the bandwidth requirement would be uh, higher as compared to the backward error correction. But the return channel for acknowledgement or for the information about the delivery would not be needed for the receiver. Redundant data sent by transmitter is also called error correction code. The additional data which is appended with the original data, that data, as we know, is called redundant data, but for error correction we call that data error correction code. In the process of error correction, some predetermined procedures are adopted by the sender and receiver, and this predetermined procedure is used to design the redundant bits, to design or calculate these redundant bits. And these redundant bits are added to the transmitted information or the information which has been transmitted from sender to receiver. Each single bit in these redundant bits will have some importance, and that single bit may have a function of many parts of the original data. Means that suppose we are adding 4 bits with the original data, so one single bit may affect multiple bits in the original data. So, backward error correction, the correction by retransmission of data. When the receiver detects an error in the data received, it requests back the sender to retransmit the data unit. Forward error correction, correction at the receiving end without retransmission of data from the sender. When the receiver detects some error in the data received, it executes error correcting code which helps it to auto recover and to correct some kinds of errors. There are two main categories for the error correction algorithms. These are block coding and convolutional coding. In block coding, we have an example that is Hamming code, and for convolutional coding, we have Viterbi algorithm. Block coding works on fixed sized packets of bits. like 8 bits, 16 bits, 13 bits, 11 bits. So there would be a fixed size, a fixed number of bits in a block for block coding. In the convolutional coding, there is no fixed size blocks. The sizes may vary from time to time or from different senders. The message comprises of data streams of arbitrary length, and a sequence of output bits are generated by the sliding application of Boolean functions to the data stream. So, in this mechanism, the algorithm deals with a stream of bits, and that stream would have an arbitrary length of bits or variable length or random length of bits, and the sliding application generates the error correction codes continuously. Now let's start the Hamming code. In Hamming code, we provide some additional bits. These bits are known as parity bits, and we specify some particular places for the parity or the redundant bits in the block. And with the help of these bits, we detect and correct the errors in the transmitted or the received data at the receiving end. So if we look into this block here, we have 4 bits received, and with these 4 bits we have three redundant bits or parity bits. So with the help of these 3 bits, we can judge the status of these 4 data bits, and if there exists in any if there exists any error, then that error can be corrected with the help of these bits. Hamming code is a linear error correcting code named after its inventor, Richard Hamming. Hamming codes can detect up to 2-bit errors and correct single bit errors. We will see that how the detection and correction take place by having an example. This method of error correction is best suited for situations in which randomly occurring errors are likely, not for errors that come in burst. Hamming code can be applied to any length of data to find and correct errors. So, for each length, we will have a particular number of redundant bits. It doesn't mean that for all lengths there would be a single set of additional bits. So these are the steps for calculating the Hamming code. Step number 1, calculation of the number of redundant bits. So we must calculate the number of parity bits for the given data bits. Number 2, positioning the redundant bits. So where these redundant bits should be placed in the data which is provided. Number 3, the step number 3, calculating the values of each redundant bit. Then what should be the value of parity bit or redundant bit which is placed in the data bits, in between the data bits. I'm quickly clarifying these 3 steps with an example. So the first step is to know the number of redundant bits. So how many parity bits are required? If we have, let's say we have 4 bits provided. So for this we will calculate and we will get 3. And if there are 5 bits, then these redundant bits would not be 3, it would be 4. Let's say for 8 bits it would be different. So we will know the number of redundant bits in the first step. Then the second step is about the placement. So where these bits should be placed. So we are placing these bits at number 1, at number 2, and at number 4 if we have 4 data bits. Then the third step is that what would be the values of these three bits. Here we would have some value, like here we have some values given. So for these redundant bits r1, r2 and r3, what would we should give either 0 or 1 to adjust the parity values according to our requirement. So now we are starting with step number 1 in details. If the message contains m number of bits, the data bits, and r number of redundant bits are added. The m can be 4, 5, 6, 8, 16, 32, any number of data bits. So we must add some additional bits denoted by r. Since r bits can indicate 2 power r states, 2 power r must be at least equal to m plus r plus 1. So the formula or the equation should be 2 power r greater than or equal to m plus r plus 1. Now let's say we have 4 data bits. So for 4 data bits we must, so for 4 bits we must have the equation like this. Now if we put 3 here, then this equation would be satisfied. It would be 8 greater than or equal to 8. Let's say we have 7 data bits. So for 7 we must provide a value of r that satisfies this equation. So here I must give 4, 2 power 4. So it would be, this is greater than or equal, should be 16 greater than or equal to, this one should be 4 here for r. So it's giving 12. So for 7 bits the value of r should be 4. We can provide 4 redundant bits. For 8 it is also possible 4 bits, and even for 9 additional bits we can give 4 for 9 data bits we can give 4 redundant bits, and it would be up to 11 data bits plus 4 redundant bits plus 1 should be less than or equal to 2 power 4, and this equation is satisfied. So for 11 data bits, up to 11 data bits, we can give 4 redundant bits. So in this way we can calculate the number of redundant bits. Let's say we have 30 data bits plus, this would be r plus 1. So if we give the value of r equal to 6, then it would be 2 power 6. This is equal to 64, and here 6. So this would give us 37. So 37 is less than or equal to 2 power 6, which is 64. And if we give this r a value equal to 5, then the equation would be 32 is greater than or equal to 37. So that is wrong. So the least value for r is 6 for m equal to 30. The next step, or the step number 2, is about the positioning of redundant bits. The are redundant bits placed at bit positions of powers of 2, that is 2 power 0, 2 power 1, 2 power 2, 2 power 3, and so on. So the position for bits would be 1, 2, 4, 8, 16, 32, 64, and so on. They are referred in the rest of the text as R1 at first position, R2 at position number 2, R3 at position number 4, and so on. So if we look into the example here, position number 1 is given to R1, position number 2 for R2, position number 4 for R3, then position number 8 would be for R4, position number 16 would be for R5, and so on. Next is step number 3, calculating the values of each redundant bit. So the value of bit is showed that it would be either 0 or 1. Each redundant bit Ri is calculated as the parity, which we usually take as even parity based upon its bit position. It covers all bit position whose binary representation includes a 1 in the ith position except the position for Ri. Now here, if we look into this example, actually we will explain this example later. So here at position 1 we have 1 here, position 1, the I'm talking about the bits for these positions. So here we have 1 and here we have 1. So these positions are for R1 whose first bit is 1. If you look into R1, it has 1, 3, 5, and 7. Now if you look into the third bit, that is for R3 here, and for 6 and 7 we have third bit equal to 1. So R3 is taking 4, 5, 6, and 7. 4 is actually taken by R itself, the redundant bit, and these are the data bits. So R1 is the parity bit for all data bits in position whose binary representation includes a 1 in the least significant position or least significant bit LSB, excluding the first. This one is actually R1. So R1 is taking 3, 5, 7, 9, 11. R1 is taking 3, 5, 7, 9, and so on, because the bits for these positions are like their first bit is equal to 1. Then for R2, the binary bit for all data bits in position whose binary representation includes a 1 in the second position from right except 2. 2 is actually for R2. Then we have 3, 5, 3, 6, 7, 10, 11, and so on. Now if you look into this example here, second bit, this one is second bit, then this one second bit and second bit. So for R3, so for R2 we have position number 3, second bit is 1, position number 6, second bit is 1, and position number 7 whose second bit is equal to 1. Similarly for R3, the parity bit in position whose binary representation includes 1 in the third position. So we will have 5, 6, 7, 12, 13, 14, 15, and from 20 to 22, and so on. And for R4, we will check the position number 4 in the bits. For R5, we will check the position number 5 in the bits from right side. So these are the three steps in the Hamming code algorithm. Now we will have an example. Calculate Hamming code word. We can also call this thing, the calculated thing, as the code word. Now this is actually the code word, data plus the parity bits. This is called code word. So calculate the Hamming code word for 1010. This is the data which has to be transmitted. So if we put this data in the table, so we have D1, D2, D3, and D4. So these are the 4 data bits. Now we are going to calculate the Hamming code for this data, or Hamming code word for this given data. Step number 1, calculation of the number of redundant bits. How many R's are required for these 4 bits? So M is equal to 4. We have 4 bits, so M is equal to 4. So the formula is 2 power R should be greater than or equal to M plus R plus 1. So here we are putting the values in the formula. We have M equal to 4. So what would be the value of R? So this equation should be satisfied. The least value for R, not only the value, the least value. So we are giving R equal to 3. So if we put R equal to 3, we satisfy this equation. We can also put R equal to 4, but that would not be the least value. So we must put the least value. So according to this step, we must have 3 redundant bits. R1, R2, and R3 are required for 4 bits that are denoted by M. So the next step is positioning the redundant bits. So here we are giving positions to R1, R2, and R3. Now if you look into the step number 2, the positions for bit is the power of 2. So the positions should be 1, then 2, 4, 8, 16, 32, 64, 128, and so on. So here the positions are 1, 2, 4 according to this example, or according to the provided 4 bits. If we have a larger number, then R4 should be here at 8 and R5 should be at 15. Then step number 3, we are giving bits to these positions. So here we have 3 bits for each. Since we are using 3 R's, so the bits would be 3. If we have R4 here somewhere, then here we must give 4 bits. So for R1, we must look into the first bit in all these positions. So if the first bit is equal to 1, then that is a part of, or that is considered by R1. So this one is R1 itself. Here first bit is equal to 1, 3, then this is equal to 0. This is not part of R1. This one is equal to 1. So this is for R1, and this one is equal to 1. This is also for 1. So R1 includes 3rd position, 5th position, and 7th position, because here the first bit is equal to 1 in all the positions. For R2, we will look into the 2nd position. So this one position is equal to 1. for number 3, and this one is also equal to 1. This one is also equal to 1 for 6 and 7. So for R2 we will have 3, 6, 7. For R3 we look into the third position, so it should be equal to 1. So this one and this one and this one, 5, 6, 7 are included with R3. If we have R4, then we must look into the fourth position of bit. We will have 4 bits, so we will look into the fourth position for R4. If we have in any example, then we will look into fourth position and put those values with R4. Now if we look into these parities R1, R2 and R3, these can be represented by a diagram. So here we have R1, this one is actually P1 R1. We can also use RRP, both are possible. So if we look into R1, 1, 3, 5 and 7 are present in R1. In R2 we have 2, 3, 7, 6. Now here we have one interesting thing. 1 is only present in R1. 2 and 4, they are also only present in R2 and R3 respectively. Now if we look into 5, so this is present in R1 and R3 only, but not in the all, and also not present in this one R2. If we look into 7, this one is present in all the 3 blocks. So by looking into this diagram, we can easily know that which bit is present in which block or blocks, and in which blocks or a single block it is not present. So each bit can be identified very easily. So what we do, we add parity bits to R1, R2 and R3. Now if you look into data, it is 1, 0, 1 and 0. This one is data. So we need even parity. So for 3, 5, 7, we have bits 1, 1 and 0. 3, 5 and 7. We have 0, 1 and 1 from right side. And to make it even or even parity, we must put the value of R1 equal to 0. So this 0 is added. Then for R2, we will look into the values of 3, 6, 7, 3, 6 and 7 and put the bits here 1, 0, 0. This is 1, then 0 and 0, and then it just its parity to its even parity. So for R we are giving 1. So if we put 1, then it would be even parity. The number of ones here is now even, and we put R2 equal to 1. After that, for R3 we are looking into 5, 6 and 7. So the bits for 5, 6 and 7 are 1, 0 and 1. So these are already even, no need to put 1 here. So we are giving 0 to R3. So this thing is the code word calculated by using Hamming code algorithm. So the data to be sent is 1010, and after the entire procedure of Hamming code or the Hamming code algorithm generation, this data will be transmitted. This is the code word generated by the Hamming code algorithm. This one is the data. This one is the Hamming code word. and received data, for example, let's say is this one. Now if you look into this data, it has an error. This one bit is different from the sent, and we can say this, that we can say that this is a single bit error. Now let's check how this error can be detected and corrected at the receiving side. So the received bits are these, and now we are detecting and correcting the error. If we put these bits in order from 1 to 7, then we will have R1, R2, and R3 here. So for R1 we have 1357 as we did at the center side. R2 we have 2367, and R3 has 4567. In R1 there are 1, then 1, and for 3 we have 0 and 0. So we have 1100. Even parity is required. This one is correct. For 2 we have 367. So here we have 7, this one, 6, this one, and 3, this one, and 2. So this one is not even, so it is not correct. Means R2's value is given in odd parity or not even parity. For R3 we have 567, so it should be even. It should give us even parity. For 567 we have 111, so 111 here, and the R3 is 0. This one is also not even parity. The number of ones is odd, not even, so this test is also wrong. Now first one is correct, R1 is correct, R2 and R3 are wrong. So here we can detect this in a very simple way by having a question: which bit is present in R2 and R3 only? By only we mean that it shouldn't be in R1, R2 and 3. It shouldn't be in R1 and R3, or in individual R's. So here if we look into R2 and R3, here we have R3 and R2. So this one is R2 and this one is R3, two blocks. So which bit is present in R1 and R2 and R3? Let's say we take 7. This is present in both, but this one is also present in 1, so we cannot take 7. Let's say we take 3. It's only in R2 and R1. It's not correct. Now if we take the bit position number 6, it is present in R3 and R2 but not in R1, and also not in all these, or also not only in R3 or only in R2. So this is the only bit which is present in R3 and R2. So bit number 6 is the only bit which is present in R2 and R3. Now if we change this bit to 0, then we will correct the received data. This data can be processed by the receiver. Now let's correct this bit. So if I make it 0, then it would be 0 here, and this would not be wrong, this would be correct, and also this would be 0 because 6 is 0 now, so this one is also not wrong, and this one is now correct. So 3 cases are correct. It means that bit number 6 or bit at position 6 got corrupted, and this one can be repaired or can be corrected by looking into the values of these parity bits or these redundant bits. This was all about the error correction. So in this lecture, we started with the error detection. Actually, this was a sort of revision for our previous lecture. So we first looked into the single bit error, burst error, error detection mechanism, then VRC, LRC, CRC, and checksum. We also studied about the parity bit, and after that we started with error correction. Then we have two approaches: the backward error correction and forward error correction. Backward means the retransmission of data from the sender side, acknowledge the sender that the data is received or not, the data received is corrupted or not, and according to that the sender will retransmit the data if required. And forward error correction is the error correction at the receiving end. There is no need of retransmission. Some additional data is sent with the some additional data which is capable for error correction is sent with the original data, and with the help of that additional data, the receiver corrects the detected errors if there are any. Then we looked into the block coding and convolutional coding. In block coding, we have Hamming codes. So we studied about the Hamming codes. In Hamming code, we have three steps. We also looked into these three steps and took an example. And according to these three steps, we processed this example. And this was all about the error correction. I hope you will do study this by yourself. And if you have any question, you can put your comments in the KCMS. Thank you.